So yesterday we derived the cable equation, which is which describes signal propagation on a passive cable, like what you have in a dendrite. So in the case of Hodgson-Huxley model, we have seen that we have these voltage sensitive, voltage dependent channels like sodium, potassium, and because of that, you have action potentials generated, which requires some kind of active energy sourcing. You need to inject energy into the signal to be able to produce that kind of a signal. But whereas if you have only passive elements, like ohmic resistance and all that, then you will have a lossy propagation, right? So, so if you don't have voltage sensitive channels, what kind of equation do you get? We have derived that in the last class. So today we'll try to we'll make a beginning at solving that equation. So we'll start with assumption of steady state conditions, right? So that we can remove the temporal variation, time variation. So then if we do that, then we can replace V of x t with just V of x. Where at steady state, we'll assume that all voltage is constant everywhere. So it becomes a purely a function of space. So if you assume that steady state condition, then you can ignore dou Vm by dou t term. So you're just left with the spatial derivative on the left side is equal to Vm minus Rm Ixt. So under what conditions shall we solve this equation? So for that, if you want to see some kind of a voltage distribution, right? If you just have a cable without any external input, then the voltage will be zero everywhere. So you need to inject some current to be able to produce some voltage distribution. So the simplest kind of current input is where you inject current at a given point in the cable. So therefore, it is a point source in spatially, right? So it's a kind of some, and it should be a constant current. So it's a point source spatially, and temporally it's a constant current. So we'll represent it as a step input in time. So if you inject current like that in an infinite cable, what is the voltage distribution like? And like I said in the last class, biologically what this corresponds to is, right, if this is your dendritic cable, because we said this cable represents a dendrite, and if you have a synapse, and when you have a neurotransmission here, the release of neurotransmitter basically amounts to injecting some current, right, I of x. So this is an idealization of that. And instead of assuming a finite cable, which is more complicated mathematically to analyze, we'll start with an infinite cable and then slowly work our way towards more realistic versions of the cable. So the external current is given by Ix is equal to I naught, a constant, times delta x. So it's a delta function in x. So it shows it's a point source. And ut represents a step function, right? So sorry. So ut is equal to 1 for t greater than equal to 0 is equal to 0 otherwise. Okay, so it's a constant and a constant current and a point source. Now boundary conditions are very simple. At x equal to infinity on both sides, right? So mod x equal to infinity, v of x t is 0 for all time, right? And initial condition is the voltage is 0 everywhere initially, and then you inject the current. So since it is steady state, we'll assume that the temporal derivative is 0, dou Vm by dou t equal to 0. So therefore, the equation is left, it becomes just this, equation 9. Lambda square dou square Vm by dou x square is equal to Vm minus Rm Ixt. Since it's a second order differential equation, so in fact, originally it is a partial differential equation, but now we got rid of the time variation. So in fact, you can even write this equation 9 in terms of normal derivatives. Lambda square b square Vm by dx square is equal to Vm minus Rm Ix. So it's a second order differential equation, linear differential equation. So the solution to that can be of the form this Actually, there's a small mistake. It should be x by lambda. Okay, so lambda is a space constant. So in fact, you can notice here that by assuming a new space variable, x is equal to small x by lambda, right? You can absorb lambda into x, and you can get rid of that parameter. So I just want you to note that, and which is what we are making use of here, right? By the variable here is x by lambda. So you can write the solution in terms of the sum of two exponentials, a into e power x by lambda plus b into e power minus x by lambda. Okay, so if you plug this in, it can be made to satisfy the equation 9 by proper choice of a, but there's a small fundamental problem, which is that look at this expression, right? This expression tends to 0 at plus infinity, right? So if you so because we said that the boundary condition is 0 at both sides, at both ends, at plus infinity and minus infinity. Therefore, since it has to go to 0 at plus infinity, you will end up with a equal to 0. Plus infinity, if it has to go to 0, this term will go to 0, but this will go to infinity. Sorry, this will go to infinity, but this term will go to 0. Okay, so a has to be 0, right? And so this will go to infinity plus infinity. This will go to 0. So for the whole thing to go to 0, we have to make a equal to 0. Similarly, at minus infinity, since Vmx has to go to 0, you will have to have b equal to 0. So you have an absurd result, because to satisfy the boundary conditions of v going to 0 at both infinities, you will end up with an expression where the whole thing is 0, which doesn't make any sense. So this difficulty can be overcome if you assume a solution like Vmx is equal to v naught into e power minus mod x by lambda. So this expression looks like this, like that tent that we have depicted in the last class. So this is origin. This is some kind of a maximum value v naught, right? So it has exponential behavior, but only thing is the sign changes on either side. Okay, so on the left side it is e power x, and right side it is e power minus x. So that's the kind of thing you have. So if you, and also we have seen yesterday that even intuitively this makes sense, because if I have a cable and if I inject current at a given point, at that point you'll have peak voltage. There's a lot of current going in, and current leaks out everywhere. So as you go away from the point of injection, the voltage keeps dropping. So that's the kind of thing you would expect intuitively. So maximum value at the point of injection and falling on both sides and going to 0 at infinity, because that's a boundary condition. So this expression kind of matches that intuitive expectation. So let us plug this in and then see what happens, right? So you need to substitute this formula into this equation 9, right, and see what happens. So for that, first we need to calculate the second derivative with respect to x. So let's calculate the first. Let's calculate the first derivative. So you get minus v naught by lambda times e power minus mod x by lambda. Now you have to take derivative of mod x, right? You know that d by dx of mod x is equal to signum x. So we have used that here. And if we differentiate this again, right, you get a more complicated expression. V naught by lambda square times e to the minus mod x by lambda minus 2 v naught by lambda times e power minus mod x by lambda times delta x. Because the derivative of sin x with respect to x is 2 delta x, because its sin x looks like this. So derivative is 0 everywhere except at the origin, where it has a discontinuity of value 2. So that gives you derivative here becomes delta x, 2 times delta x. Okay, and so that's why you have 2 times delta x here in the second term. Now, the second expression can be simplified further by invoking this formula. F of x delta x is equal to f naught times delta x, because delta x is 0 everywhere except at 0. Therefore, if you multiply it with some f of x, it doesn't matter what f of x is at other points other than 0. Right? At 0 alone, it will survive. At the other places, it will die. So this is equal to f naught times f at 0 times delta x. So we plug that in here, therefore you get e power 0 minus 0 by lambda. So that becomes simply, the second term becomes minus 2 v naught by lambda times delta x. And one more assumption we made here is one more equation that we used here is sin x square is equal to 1, because if this is 1 for positive side minus 1 for negative side. If you square it, it becomes 1 everywhere except the slight problem at the origin, but otherwise it's 0 everywhere. So if you make all these assumptions, I mean, if you insert all these results, you get this formula, this expression. So therefore, now if you multiply both sides by lambda square, you get lambda square dou square Vm by dou x square is equal to V naught times e to the minus mod x by lambda minus 2 V naught lambda times delta x. So this is what you have. And you can notice that this is identical in form to equation 9. Sorry, left side is exactly the same. Right side is Vm minus Rm times Ix here. Right side here is, this is actually Vm, the solution that we assume. Right, and the second term here is supposed to be minus Rm times Ix. So this is equal to minus Rm times Ix. And Ix is V naught times lambda x. So therefore, if you plug that in, if you compare those two terms, you get V naught is equal to I naught into Rm by 2 lambda. So what this formula gives us is, it gives V naught in terms of I naught, because I naught is the magnitude of the input current, right? And V naught is the peak voltage at the point of injection. So based on the input values, I'm trying to find important parameter of the output. So output, ultimately you want the entire voltage distribution over the entire cable. So the key parameter there is V naught, which is the maximum value at the point of injection. You got that. So if you plug this back into the formula, you get Vmx is equal to, substitute, instead of V naught, you substitute this, you get I naught Rm by 2 lambda times e power minus lambda by minus x by minus mod x by lambda. Also note that we've defined lambda before is equal to root of Rm by Ra, which if we expand in terms of these intrinsic variables or intrinsic parameters, capital Rm by capital Ri times d by 4, where d is the diameter of the cable. Now we need to define a quantity called electrotonic length or electrotonic distance. Right, we will use this later when we derive similar results, voltage distribution results for finite cable. So like I said, this kind of substitution is natural because in the equation itself, right, like I said, if I assume a new variable, capital X, which is equal to small x by lambda, I get a dimensionless distance or a length variable. If I plug it in here, I can write this equation in terms of this capital X, and lambda goes away. Right, so that's very convenient. So therefore, it is natural to define a kind of a new distance variable. So if a cable is of given length capital L, small l, then we'll define a new length which is scaled by this space constant as by taking the ratio of small l by lambda. This is called electronic distance or electronic length. Now another quantity we'll define here is input resistance of the cable. So I have this infinite cable. I inject some current. Okay, so I naught, and I get some voltage here. So voltage here is V naught. So can I make this equivalent to and I make the entire cable equivalent to some resistance. I'll call this Rn. So if I replace this cable, right, with some resistance, I should not see any difference. I should get the same, so the same voltage. What is that resistance? Right, that's the definition of input resistance. So basically, that is nothing but V naught by I naught, right? Yeah, it should be some resistance which will produce a voltage of V naught. Then you won't see any difference. So V naught by I naught, as we have seen here, will be is nothing but Rm by 2 lambda, right? So V naught by I naught is equal to Rm by 2 lambda, which is also equal to root of Ra Rm by 2 lambda, because I'm invoking this result. Lambda is equal to root of Rm by Ra. Right, I'm invoking it here. So you get this, or this also can be written as Ra lambda by 2. So basically, there are three alternative forms of the input resistance. So given the cable parameters, right, these per unit length parameters, then I can express the input resistance of the cable by any of these formula. So simple example, just to give an idea. So let us say I'm injecting a current of 10 milliamps, right, at a point x equal to 2, right? Then the equation is given by this. So I'm defining the length around that point of injection 2. Okay, so the plot will be, so this is the formula. You just plug in the values and you get an expression like this. Now, so that's the kind of voltage distribution you will see in case of an infinite cable. An infinite cable is obviously not practical, right? Because real cables are finite. So what we will do before we go to a fully finite cable, we take something called a semi-infinite cable. So it is infinite only in one direction, right? So it's like you have the mouth here, the other end goes off to infinity, and I inject current here. Which means something like this. So Ix is given here. So again, if you have the same kind of a cable, same kind of parameters, Ra, Rm, and all that, right? What is the input resistance and what is the voltage distribution? So these are the, so what is Vm of X for such a cable and what is Rn for such a cable? So let us see that. So for this, we don't have to solve the equation again by just using the same result for the infinite cable. We can just throw a little hack and get the result for the semi-infinite cable. If we take an infinite cable and split it into two, you get two semi-infinite cables, like what you see in this figure. So if I'm injecting current of I naught into the main cable, into the two halves, I'm effectively injecting currents of I naught by 2 and I naught by 2, because for reasons of symmetry, because both sides are identical. So which means if I inject current of instead of I naught by 2, if I inject current of and so basically if I, in this situation, right, I'm just treating the main cable as being consisting of two semi-infinite cables. So then in the original cable, I have a voltage distribution which goes like this. Now in the two half cables or the semi-infinite cables, I'll have voltage distribution like this. Okay, so this is what we get, and the voltage here is just the same V naught, right? So for a semi-infinite cable, even if I give a current of I naught by 2, I get a voltage of V naught. So therefore, if I give a current of I naught, I'll get a voltage of 2 V naught because it's a linear cable. The whole structure is linear, right? So that's what you have. In the previous one for V naught, we have I naught Rm by 2 lambda. So now you have twice that voltage for the same current. So I naught Rm by lambda times e power minus lambda by x, uh, which is, you have to take. So it only depends on the magnitude of x, right? We'll keep the same formula, and therefore for the resistance also it is twice that of the infinite cable, because if you look at this arrangement, so each of them has some resistance. right? Let's call this RSI, so resistance of semi-infinite cable. Now these two resistances are in parallel, right, as you can very easily see, because this voltage is V0, and both of them end in the voltage 0, because it is V0 is 0 here and V0 is 0 here, so that's the ground. So both these resistances are in parallel. So this is RSI, so this is RSI, and this whole resistance, as we know, is equal to Rin that we calculated before, right? With these three quantities. Therefore, RSI, individual RSI is input resistance is twice that of the infinite cable. So Rin now simply becomes Rm by lambda, right? Or square root of Ra Rm or Ra times lambda. Now this R infinity for the semi-infinite cable, right? We'll call this. So this Rin for semi-infinite cable, we'll denote this by the notation of R with subscript of infinity symbol. So this R infinity is called input resistance of a semi-infinite cable. Because we give this special notation because we'll express other quantities later. So we'll derive input resistances of finite cables later. And we will express the result in terms of R infinity of the cable. So therefore, let us remember this notation. So that gives us a couple of results, right? We started with discussing the infinite cable, right? And then we derived the voltage distribution and the input resistance. Next, we derived the voltage distribution of the semi-infinite cable and the input resistance. So then let us look at slightly more realistic versions. Let us go to a finite cable. So let's take a finite cable of length small l, right? And just a moment ago, I defined this new quantity called electrotonic length, which is basically a dimensionless length scaled by lambda, the space constant lambda. So it also this is the length of the cable, right? And similarly, the distance or the space variable x is also now replaced by capital X by this equation. So capital L is equal to small l by lambda, and capital X is equal to small x by lambda. We'll define this new length or distance variables, and we will define even the solution. So earlier we had solution in terms of so the earlier solution was like uh, a into e power minus, so it means for x by lambda plus b into e power minus x by lambda, because that's the kind of solution we had, right? This is earlier for infinite cable. So now what we will do is we'll replace this with a new kind of expression where so we'll use this for finite cable. Right, we'll define this in terms of the hyperbolic functions cos h and sin h. So as you probably remember, cos h is given by e power x plus e power minus x by 2, and sin h is given by e power x minus e power minus x by 2. Right, why do we have to do this? Because same equation, right? The equation hasn't changed, therefore the same expression in principle should work. And also you can easily see that cos h and sin h are basically linear sums of the same exponentials. So in the original expression, which is a linear sum of exponentials, e power x and e power minus x, cos h and sin h are both such linear sums. So why bother? So let me explain that in a moment. So these are the two expressions, and the cos and sin h has an interesting property. Derivative of cos h is sin h, and derivative of sin h is cos h. And unlike sine and cos, where derivative of sine is cos, but derivative of cos is minus sine, right? You don't have that minus sign showing up here. So cos h looks like the middle function, right, going to infinity on both sides. So these are not bounded functions, unlike sine and cos. And it is 1 at origin, and sin h is a So you can also see that cos h is an even function, sin h is an odd function going through the origin. So it's 0 at 0. And tan h is a sigmoid function. This is finite, it's bounded. Whereas tan x is unbounded and goes to infinity. And analogous to the equation sin square x plus cos square x equal to 1, here we have cos h square x minus sin h square x equal to 1. Okay, so some basic results of this. So the thing is here, sin x and sin hx is 0 at 0, right? And you need that kind of a result because when you have a finite cable, sometimes you might have a boundary condition. So this is the input. Current is injected here, Ix, and there's some voltage here, V0. It can so happen that the voltage at the other end is 0 or current at the other end is 0. So you can create boundary conditions where some quantity, either voltage or current, can be made to go to 0 at the other end. This is L, and this is x equal to 0, this is x equal to L, capital X equal to capital L. Now, whereas if you use only these, e power x and e power minus x, you can't make it go to 0 at a finite length because it's simply not convenient. So, whereas if you take cos h and sin h, and are equivalent in the sense they are also linear sums of e power x and e power minus x, by choosing a function form like this, cos h of L minus x and sin h of L minus x, at x equal to L, right, at the far end of the cable, I can make sin h go to 0, right? So I can easily, the math works out to be slightly simpler if you use this kind of expression instead of the original e power x by lambda and e power minus x by lambda. So let us look at finite cables, and we'll look at three kinds of finite cables. The first two are special cases. The third one is the most general. Because when you have a finite cable, you need to define boundary condition. So that is, boundary condition is what happens at the far end of the cable. How do you set the, so what is the current there, what is the voltage there, and what's happening there. So here we will, and biologically speaking, in physical terms, a finite piece of cable, it doesn't make much sense if you take it all by itself, because a small piece of dendrite with nothing before, nothing after doesn't make any sense, right? So, but if I have some kind of a loading resistance after that, I'll call this RL. That resistance can represent everything else that you have downstream. So let us say I have a dendrite which branches out into a bunch of branches, right? So I'm considering a small segment of it here. This part represents my so-called finite cable. Now, so I'm injecting some current here. Let us assume for simplicity right now there is none of this stuff before it. Right? The whole thing starts here. But there's a lot of stuff after that finite segment. So whatever you have after that, let's assume for now that I can replace this whole thing, right, and substitute it by simply a resistance. I'll call this RL. So like that, I can make a substitution and and represent the whole thing as some resistance, right? So that is how we'll justify the relevance of studying a finite cable. A finite cable with some loading resistance is widely general, but a finite cable without anything is too artificial. And also there's a problem of defining the boundary conditions. So what happens if I just leave the other end dangling like that without having anything there? So to take care of that, we'll first consider two cases, right? Where in the first case, I'll assume that RL is infinity. That is, the circuit is open. So RL is infinity means I have the cable at the far end. I just have, it's an open circuit, right? The current can't pass. There's infinity. The other case is RL equal to 0, so it's a short circuit. So which means at the other end there's just a straight wire into the ground. The third case is the most general one, which is what you are seeing here. Right, there is a finite resistance of value RL. Right, so let us look at these three things. So we call the terminology here in Christoph Koch's book is the first case where RL is infinity, he calls it the sealed end, right? And the second case where it is zero, he calls it the killed end. The third case is arbitrary. It can be any resistance. So now why do we use this kind of weird terminology? Let me explain that in a minute. So let's consider the first one, the sealed end boundary condition. So here it refers to a situation where the dendrite is sealed or closed with a membrane patch. So if I take a long dendritic tree, right, with lots of branches, if I look at the very tip of a dendrite, right, at this point it looks something like this. Because dendrite has a membrane coating, right, this covering of a membrane. Membrane is a great insulator, right? So in the cytoplasm is more conducting, but membrane is a great insulator. So right, therefore, if you can think of this small patch at the tip of the dendrite as a resistance of a high value, right? How high? So just to take some sample numbers and calculate the possible resistance there. Let's take a cable or a dendritic cable of diameter 2 microns. And this is a typical diameter. These are very small cables, very thin cables. Now Rm membrane resistance, because to calculate this resistance, we need to know the resistance of the membrane. This is membrane resistance. It is 10 power 5 ohm centimeter square. And that's a typical value. Therefore, if you take Rm by the area, right, you get RL, which is 3000 gigohms. It's a huge resistance. So you may practically consider it as an open circuit, right? Because not much. So current will flow up to this point, but doesn't go beyond. I mean, what that means is current will flow out because you'll have ion channels all along. Right, the tip there's just this patch of membrane, and not much goes out. So we'll approximate it as with the boundary condition II is equal to 0. So II is the actual current, as you know. So at the sealed end, where capital X is equal to capital L, we'll assume that II is equal to 0. So that's the boundary condition for the first one. When we call it the sealed end. The meaning is quite obvious because it's sealed. Now, how do you mathematically work out the implications of this? When this boundary condition is true, what happens? So we know the formula for II, right, which is given by dou Vm by dou x is equal to Ra times II. We derived this in yesterday's class, right? So therefore, this left quantity is proportional to the II, and II is 0 at x equal to L. Therefore, dou Vm by dou x at x equal to L is equal to 0. So then what happens? What is dou V by dou x is equal to minus sin h of L minus x, right, minus b cos x times L minus of L minus x, the whole thing by lambda. How did we get this lambda? Because we have to differentiate. So you see that the derivative is with respect to small x, because the original equation, the differential equation, is in terms of small x, the original space variable small x. Whereas I am expressing the solution in terms of capital X. So capital X, which is electrotonic distance. Therefore, when I differentiate, I need to make sure that I take care of this difference, right? So x equal to small x by lambda. So therefore, dx is equal to dx by lambda. So that's how you get lambda in the denominator here. So this is equal to 0, and if you plug in x equal to L, the first term here becomes 0. So you get only the second term, which is equal to 0. Therefore, B is equal to 0. So if B equal to 0, then your original expression for voltage, which is A cos h L minus x, B sin h L minus x, right? This becomes B equal to 0. Therefore, it becomes P of x is equal to A cos h L minus x. So the boundary condition with the sealed end, where II is equal to 0 at capital X equal to capital L, that gives us a slightly reduced expression for the voltage like this, A cos h L minus x. Now we'll make one more assumption, introduce one more parameter, V naught. which we'll say is we define as the voltage at the near end at x equal to 0. Both small x and capital X is equal to 0. Then if you plug that in here, this equation, then you get V naught is equal to A cos H L. So you can see that here, right? And therefore A is equal to V naught by cos H L. And if you plug it back in here, you get Vmx is equal to V naught into cos H into L, cos H of L minus X by cos H L. So this is the voltage distribution for a finite cable with sealed and boundary condition. So now we need to find out input resistance. So how do you do that again? So basically you need to find out the input current, right? And then V naught by II at the input. That gives you the input resistance. So how do you do that? Again, we know that II is equal to minus 1 by RA times dou Vm by dou X. So again, if you differentiate Vm, you get V naught by, so this is, sorry. So this is the Vm, right? This expression. So if you differentiate that, you get V naught by cos HL times minus sin H L minus X times minus 1 by RA lambda. So you get this. So if you take X equal to 0, you get the input. This is the expression you get. This is II. Therefore, V naught by II is equal to, so V naught by I at X equal to 0. So you get this. So R infinity, R in input is equal to R infinity times cot H L, right? You know, 1 by tan H is cot H. So you see that the input resistance here is expressed in terms of R infinity. That is, if you had a cable of the same parameters, RA and RM, right, but of infinite length. Okay, so then that the input impedance of that is R infinity. Now, if I take a cable of the same kind, of same material properties, but of electrotonic length equal to L, right, then I can express R in of this cable in terms of R infinity by this formula, R infinity times cot HL. Okay, so similarly, let us derive the input, the properties, the voltage distribution and the input resistance for a finite cable with killed end boundary condition. What is this killed end? I mean, why do we use that kind of violent language? So the explanation is, in case of sealed end, we have we have the dendrite is closed. We are looking at the tip of the dendrite, where the membrane offers high resistance. So we treat that boundary condition as an open circuit. So we do the opposite in case of a killed end. So in killed end, basically imagine that I take a dendritic cable, right, and then chop it at a given point. Okay, just for sake of argument. So then what happens is the cytosol comes into contact with the extracellular space, right? So therefore direct contact, this earlier high resistance patch of the membrane is now gone. So both cytosol and extracellular space are in now direct contact. So resistance offered is very little, right? So I can treat it as a short. So therefore that is like taking RL is equal to 0. So they call this the killed end because it's like you're killing that end, you're chopping off the end. And another reason it is this kind of a word is used because sealed and killed kind of a rhyme. Okay, they wanted to have something rhyme. So this is how you get this new boundary condition. RL is equal to 0. So again, we'll try to solve for Vx and Vmx and Rin in this case. It is quite straightforward, follows similar pattern as what you have done in the previous case. Again, start with the same expression, Vmx equal to A cos H L minus X plus B sin H L minus X. So boundary condition is, since it is shorted at the far end, RL is 0. So the voltage here is also 0 because it's shorted to the ground, right? So Vmx equals 0 at X equal to capital L. So if you plug X equal to capital L here in this expression, equation 14, you get a cos h 0 plus b sin h 0, right, is equal to 0, right? So that gives you a equal to 0 because this expression is 0, and then first one is cos h 0 is not 0, it is 1. Therefore, a has to be 0. Then if a is 0, then you get Vm of x is equal to b sine hl minus x. So this is the expression, slightly reduced expression than the full form. Now we need to find out b. And how do you do that? Just like before, right? You assume that the voltage at the mouth of the cable is V naught by definition, right? And therefore, if you plug it in here, so at x equal to 0, V naught is equal to b sine h of L x equal to 0. So therefore, b is equal to V naught by sine h L. So if you plug this back in here, you get V naught Vmx is equal to V naught into sine h L minus x by sine h L. Now, how do you find the input resistance? Again, just like before, you find the input current and then do V naught by II at input, you get the input resistance. So input current is given by this Ra times dou Vm by dou x at x equal to 0. So you get dou Vm, so dou Vm by dou x is equal to this whole thing. Because we know that Vm is equal to this right now. Okay, and if you set x equal to 0 in this, you get, and if you also have 1 by Ra, sorry, it should be 1 by Ra, right, you get this expression. Now, if you take V naught by II, right, Rn is equal to V naught by IA, you get lambda Ra times tan h of L. Lambda Ra we know is equal to R infinity, so that is tan h of L. So again, we are able to express the input resistance in terms of the R infinity of the cable, right? So since the fact that the cable is of finite length comes through in this part of the formula, right? So basically, you can also verify this. That is, if L is equal to infinity, right? This formula should give you R infinity, which is true because tan h of infinity is equal to 1. So you recover the same formula. Okay, so that completes our discussion for today. That we were able to derive the expressions, voltage distribution, and input resistances for actually 4 kinds of cables: the infinite cable, semi-infinite cable, and finite cable. With two varieties of, that is, with 2 different kinds of boundary conditions, one with sealed and one with killed end. So then we are ready to derive the expression for arbitrary boundary condition, where there's a loading resistance of value RL, but that's a bit more involved. There's a lot of algebra to work out. So let us do that in the next class on Friday. Okay, any further questions?